Before we get into our ideas with theoretical probability, I want to set our notation a little bit more carefully, that we're saying a probability experiment is whatever thing with uncertainty we're trying to describe here. It can be a little bit more exacting in terms of what we're looking at, but I'm trying to be loose here with the word thing because there are some important other words in here that I don't want to step on and give the wrong idea for, where we say the sample space is the set of all possibilities that can possibly occur, which is in terms of like a deck of cards, all the cards, or maybe all the cards twice if we're taking two, but that's getting a little bit further on. The point is, when we're looking at the sample space, we're looking at any possible thing that can happen, and then an event is said to be a subset of the sample space, but really, the event is the thing that we happen to be looking at. It's the outcome that we happen to be looking for, or set of outcomes that we happen to be looking for from the sample space in our experiment. Where, if we want to find the probability associated with some event E, and we're following theoretical or classical probability, the rule is that P of E, the probability of event E, is given by the number of ways we can have E divided by the total number of things within our sample space. So, this is the sort of thing that we do when we're talking about things like coin flips, dice rolls, basically the standard set of events that you might expect to talk about here. A lot of gambling stuff here, which, hopefully people do have some sense of how cards and dice work, because, well, they're great for talking about these sorts of things. Anyway, let's get a couple quick examples in this flavor so we can better understand what it is that we're talking about. For our first example, suppose you roll a fair standard six-sided die. What is the probability of rolling a 4, a 7, and a number bigger than 2? Note that when we're dealing with these sorts of things, we're going to take care of them one by one, because obviously you can't get all of these things at once, certainly not meaningfully. So in our first case there, if you want the probability of getting a 4, we write that as P of 4 is equal to the number of ways we can get a 4, in this case 1, divided by the total number of things that can happen on a dice roll. In this case, that would be 6. So the probability here is 1 out of 6, or if you want to represent that as a decimal, we would say that's about 0.167, not 1.167. That'd be more than what is possible, which is, that's a little bit hard to comprehend. So we're going to stick to the stuff that can actually happen here. And then if we want to write this as a percent, because sometimes we like writing these things as percents, we could put that in as 16.7% and have the same value meaningfully. Then for our second case, if we want to find the probability of getting a 7, hopefully we have some understanding of how dice work, where when we say fair standard die roll, what we're talking about is the numbers 1 to 6, and there's no weighting, so they're all equally likely. That's the other defined quality of theoretical probability, but probability of 7 here would be 0 out of 6, or 0, or 0%, depending on what you prefer to say for that sort of thing. Point is, it can't happen. That's, like I said, what we use when we're dealing with a probability of 0 is something that, under our assumptions, not just shouldn't happen, but actually can't happen. And then finally, for our last case, the probability of getting something bigger than 2, I'm a little bit loose with my notation here, but hopefully you get the idea that if we want something bigger than 2, we want a 3, a 4, a 5, or a 6, which means we have 4 total options out of 6 in the sample, or if you prefer a reduced fraction, 2 out of 3, or 0.0667, or 66.7%. You're going to see a lot of values that hopefully you're somewhat familiar with, seeing how these things work from previous experience. Anyway, let's get one more example here of a similar but more card-based flavor. For our second example, we want to find what the probability is of getting a jack from a standard deck of cards. So, if we want to find this probability, the probability of getting a jack, we have to understand there that in a standard deck of cards, we have 4 suits. In each of the suits, we have 13 cards. So, we have a total of 52 cards. It always surprises me a little bit how few of you guys have done anything with playing cards before when I teach these things. But as I said, they're classic examples. They're good to work with for these, where out of 52, in each suit, we have 1 jack, 4 suits, 4 out of 52, or if you prefer, 1 out of 13, because you can think of this as saying, I want the jack from one of the suits, because that's the same sort of question here. When we're dealing with our cards, the reason why they're classics is because they have a lot of nice reductions that might not be perfectly obvious, but should make reasonable sense in terms of how they interact. Where here, that's our associated probability. As I said, this stuff with classical theoretical, it's very straightforward. Exactly what you think of when you think probability. So let's deal with something that maybe is a little bit less obvious, but that still falls into the same sort of pattern here, looking at empirical probability as well.